So starting with organic chemistry of AS 14th chapter, which is basically the introduction to organic chemistry, we are really going to go with most of the stuff that was from IGCSE, but for the lesser or one third of this chapter is going to be advanced material, which is really going to be a step up. This is important because what we are about to explain to you in this chapter is going to be a part of every other organic chapter there is all the way up till chapter number 18. Okay, so let's get started. 14.1 is representing organic molecules. So these figures actually show you different representation of different molecules and their 3D models for the purposes. They are also going to start off with the definition of hydrocarbons, which you already probably know that hydrocarbons are the compounds of hydrogen and carbon only, which actually divides all the organic compounds in two major categories: hydrocarbons and non-hydrocarbons. So if there's just carbon and hydrogen, which is basically alkanes, alkenes, and alkynes, that is hydrocarbons. And apart from that, anything else would have a third atom. It can be nitrogen, it can be oxygen, sulfur, phosphorus, any of the halogens, anything like that. And that would be considered as a non-hydrocarbon based substance. So methane, ethene, benzene, octane, 2,4 trimethyl pentane, cyclohexane, propene. These are all here for the idea what we are about to face in AS chemistry. So it gives you an idea about the simple alkane and a simple alkene. Benzene is the molecule which is both singly and doubly bonded. This is really different. Benzene is so important in chemistry that we're going to create the largest branch of organic chemistry based upon benzene alone. We're going to discuss its chemistry, but most of that part is A2, that's not AS. However, we're going to give the introduction right here and now. Okay, moving on, octane. This is another simple alkane, but they are going to give you an idea that the chains can be longer and they just don't have to be represented like this. Uh, they can be represented with stick model as well. Now, 2 to 4 trimethylpentene gives you a better idea. Chains don't always have to be straight. Sometimes they have branches, and branches can really be more than one. Just having one branch on a simple chain is the idea we used to use back in ICCSE, but this is going to get complicated at this level. This also gives you the idea that you should know about the naming of how to name these branches really, which we are going to confirm is in the later part of the same chapter. So even if you don't know how to number it or name it, don't worry, I am going to cover that in the same chapter. So then we have cyclohexane, which gives us the idea that cycloalkanes and cycloalkenes, uh, cycloalkenes, if I say it would be the least or the smallest part, minimum part in this chapter would be right. However, cycloalkanes is going to be something that is going to be common in here. So this gives you the idea, no first or last carbon. Actually, every carbon is connected to the next carbon in the same line. It really gives us a very good idea about what's going to happen in this kind of compound. This is still a category of alkane, even when they are cyclic. And then propene giving us a better idea. If they might have drawn two double bonds in a single compound, we would have taken that one as a good example too, because that is something we are about to do in A levels chemistry as well. So this gives you a very good idea of space filling models, which we also call 3D models, and ball and stick models. As you would see, the first three are simply space filling or 3D models, but from D to G all the way, you have ball and stick models. Now, when we go for the ball and stick model, the easiest way to remember is that dark gray or the black color is for carbon, white means hydrogen, red means oxygen, blue means nitrogen. This really gives you the idea of the most important ones that we use. There are other things over here, but again, if you don't remember everything, you can always come back and refer to this table. You are not supposed to memorize this table at all. Okay, moving on. Remember, there were actually 5 different types of formulae that we discussed back in IGCSE, which we are going to discuss here too. So when I use the word five, combining all the categories at one place, that might seem like a big number, but trust me, we are done with five different kind of formula. So getting started with the first one, that is empirical formula. Empirical formula is the first one that we deal with, and it gives us the least detail. It tells us the simplest ratio of different types of atoms present in the molecule. An organic compound called propene has the empirical formula CH2. Basically, propene is C3H6, so it is actually simplified into this form. It tells us it has twice as many hydrogen atoms as carbon atoms, but it is not exactly giving us the exact number of carbon or hydrogen atoms, which is the basic idea for empirical formula itself. So we can calculate empirical formulae from experimental data based on the mass of each element in a sample. Sometimes we can also do it with the help of percentage composition. And all of these methods are something which you have done way past in IGCSE. And you did the same thing in the first three chapters of quantitative chemistry in AS. So I hope you clearly understand how we can convert the masses into number of moles and the number of moles cancel down to the simplest ratio to get the empirical formula. So moving on, molecular formula is the one that gives us the actual number of atoms of each type of atom in a molecule. So it gives us a really good idea. It also can tell us the relative molecular mass of the compound. Remember, from the empirical formula, we can never calculate the MR of the compound. It can only give us the empirical formula mass, which really is of any use. We may use it for calculation of molecular formula, but apart from that, it isn't of any good use for the rest of the formulas we have in the mole chapter of quantitative chemistry. So for example, if we still talk about propene, we know that the relative molecular mass is 42, and that is CH2 multiplied by 3 or 42 in the form of C3H6. Whichever way you're going to do it, it is going to give you the same answer. So both of these methods are very important. I hope you understand that CH3, C3H6 is 3 multiplied by 12, 36 plus 6 is equal to 42. But you should have a hang of this too. That's, if there were CH2s, the empirical formula for CH2, it must be 3 into CH2, for which we get the answer 42. And we get this number 3 really for the conversion as well. So we have been doing this previously in the quantitative chemistry part. So I hope you understand this kind of working already. Moving on. Number 3. Now we get a lot better detail by having the structural formula. This gives us about the details to bonds, how each carbon atom or how really any atom in the molecule have bonded. So the structural formula gives us the idea. Now, he has considered the structural formula in two different ways. Now, this really can be correct, but since the central H atom does not form a double bond, it's better to write it this way, the one written first. Okay, so you can write it like this. You may also write it like this, but that's fine. Okay, they're telling you what is the exact way of writing it. However, giving yourself a better habit is a good idea to do it. Okay, all right. So moving on. Um, yeah. The structural formula tells us how many hydrogen atoms are bonded to each carbon atom. In the case of propene, आपको अंदाजा होगा कि molecule जो है वो एक double bond से जुड़ा हुआ है. This gives us the idea that how we're going to number it. I hope, though it's attached to the naming or nomenclature method, but I hope you understand that this is how we number them. The double bonded carbons usually get the lower numbers if possible. So number 4, carbon-carbon double bonds are shown in a structural formula. However, all the bonds within a molecule are shown in its displayed formula. Structural formula is usually with that one, the one that is given in point number 3 is actually the contracted form. If I be exact, structural formula never showed you any carbon-hydrogen bond. it actually omitted those bonds. Structural formula may also omit carbon-carbon bonds at some point, only the carbon-carbon single bonds. However, it is going to show you carbon-carbon double or triple bonds, as you can see in this structure, and as you can see in these formulas. However, displayed formulae is something that we have been using a phrase for all the atoms and all the bonds. This is the phrase we have been using back in IGCSE to explain what displayed formula was all about. So displayed formula always is going to be in the same way. You need to show all the atoms, need to show all the bonds. That's how it works. You cannot skip even a single bond that is not displayed. You can't omit it. If you do, if you do, the displayed formula will be considered as incorrect. Let me explain myself by giving a very simple example. Now, most of the time we write the formula of ethanol as C2H5OH, and I've seen students expanding the C2H5 part, but I've sometimes seen them writing OH together, just they have been doing all along in the inorganic chemistry portion, right? So you might think this is the correct displayed formula, but let me tell you, since this bond is not shown, it is the incorrect one. So make sure when the word structural formula or displayed formula are written in the paper, you go exactly accordingly. Now, this is something that you might have skipped back in IGCSE, and you might not have paid attention to this little piece of detail back then. And even then, you get marks. Yeah, there is some leverage back in IGCSE, but there isn't any leverage going to be in AS. You make a mistake even if your whole structure is correct, which you can see what I've drawn is actually correct. That's not wrong. But if you're not showing all the atoms or all the bonds, or if you're omitting any one of it, you're wrong. That's how easy it is going to be. So you need to be very, very good at paying attention to the little pieces of detail in AS and in A2. So A level is a prerequisite like that. So a simplified version of displayed formula up ahead is skeletal formula. Now, all those five types that we have done previously from IGCSE have been finished. You might be considering that I have really discussed four types. I'm talking about a fifth type as well. Well, I didn't really never discuss the general formula as a type over here. So general formula was a formula that we were previously using to depict an entire homologous series or entire family. For example, all alkanes were shown to be CnH2n plus 2. So general formula really was the fifth type. Okay. So since I'm done with all five types, let's move on to skeletal formula. Now this is a simplified version. Skeletal formula actually tells us about the skeleton of the structure. This is the easiest, simplest way. But rather than saying the easiest, simplest way, I would rather say more sophisticated way. These sophisticated ways are not easy at times. In fact, they are a little bit difficult, but you need to get into a habit of going under that kind of sophistication. Now, that level of sophistication is required from you at ASNA2. So as you can see, the skeletal formula are going to be simple lines, and we are going to use all the symbols from the periodic table, but we are not going to use carbons and hydrogens. Okay, so we are not going to use carbon to hydrogen bonds either. So only the carbon-carbon bonds, whatever kind of bonds they're in place. All other atoms and their bonds are in place. So what does this mean? This means propene. You're going to understand every bend in a line that this is one carbon, this is another carbon, since this is also a bend, this is another carbon, this is also a bend. Let me write them outside. Okay. So as soon as you get it, this comes out to be a single bond, this comes out to be a double bond. So you're really going to work out the hydrogen atoms yourself, that this carbon has two bonds, so of course it has two more hydrogen atoms to complete all four of its bonds. This carbon has bonded three times already, so this is going to be really H just with it. and this carbon has only has a single bond, so three hydrogen atoms. This gives you a very good idea of how you are going to work the hydrogen atoms out. So all other atoms that are not carbon or hydrogen and their bonds are included in the skeleton formula. For example, if this was not it and this was CH2, you would understand that if they write like this, okay? So this gives you a very good idea. All right. Okay, this gives a very good idea. Butane 2-ol. I hope you understand. As soon as I say butane 2-ol, that this is one and this is second carbon. So since there are a total of three carbon atoms, but means it has four carbon atoms. N means they are singly bonded. 2 represents the carbon at which the alcohol group is joined, and ol is the suffix for alcohol group. Now you understand every single part of the name in our naming or even the numbers has a specific purpose. Don't forget that every time there is a number and a letter has to be separated, we're going to use hyphen or dash. The numbers are usually separated with the help of commas. Numbers and letters are usually separated with the help of hyphens or dashes. Okay, I hope you get that point too. So let's keep moving on. Now, sometimes you can see the zig and zag in carbon chains. I usually say that we can call them dotted lines or wedges, or sometimes these dotted structures. So, well, if you take a look at it, this gives you a pretty good idea how this is all going. And now this structure is actually a 3D representation. 3D displayed formulae, we are going to discuss them. Optical isomers in the same chapter. We're going to discuss how that works, what the dotted line or what the wedge line means. Dotted lines can sometimes be also shown as these lines, dashed lines. Well, both are acceptable. These are known as dashed lines. These are known as dotted lines. Both mean the same thing. Both conventions are acceptable, right? So since he has given us an idea right here below the diagram in the caption, so I am going to go with that idea. The wedge bond is sticking out of the plane. This means towards you. This is the third dimension, which we usually experience while watching a 3D movie, and it really is a good experience if I say that. So you would understand that this wedge is towards you, and this dash line, or maybe the dotted line, whichever convention we're talking about, that they usually use the phrase into the plane of paper, or we can say away from me. Okay, so this gives you a very good idea of how this goes. Now, with complex molecules, chemists sometimes find it useful to combine the structural, the 3D, the skeletal formula all to represent just one single molecule. For example, you might have heard the word cholesterol before. For those belonging to medical, this might be a word they might have heard way too many times. For those who are familiar with the terms of diseases, high blood pressure or other heart diseases, that we keep talking about more commonly as a part of which diet or which stuff to eat and which not to eat, this might be a name you might come across many times. Now, this is the molecule of cholesterol. Now, this entire molecule has a structural, a 3D, and a skeletal approach to it, all combined into one. And I hope this makes complete sense to you, because the wedges means the bond towards you, or the structures. It can be a single atom, it can be a group of atoms, it can be a functional group, it can be anything. When I say single atom, I mean this. When I say a group of atom, I mean this. When I say a functional group, I mean this. So I hope you understand. Okay, the same thing can be happening with the dotted lines. You may also use the dash lines. They're away from you. And for the rest of the bond, they are actually a part of the plane. Okay. Now, x-axis, y-axis is a part of plane. We have already been using those axes. However, the z-axis is divided into two categories, into towards you and away from you, right? So I hope this gives you a very good idea. And I hope if you see a question like this, you can write its molecular formula. You can count the number of atoms. Now, remember, every bend in a line, every twist, every corner is considered a carbon atom. So let me clarify when I write these, this is a carbon atom, this, these are all carbon atoms. Okay. So when I write it like this, I hope you understand some carbons are singly bonded, some carbons are doubly bonded. This is a molecule of cholesterol, and this gives you a very good idea of how the questions end that you might confront in paper one MCQ paper. The questions about their formula is pretty common. Of course, I hope you can count the carbon atoms as well as the major part or the more difficult part, if I say, would be the calculation of hydrogen atoms. You might need to work out hydrogen atoms with every single carbon atom, keeping them in mind. This might get difficult. Now remember, if the carbon has all four bonds, it does not have any hydrogen atoms again. If it has bonded already. For example, if I mark this one out, you'd notice it has all four bonds already, and none of them are going to be hydrogen atoms. So it won't have a hydrogen atom. If a carbon is already bonded to three sides, it will get one hydrogen atom. If the carbon is bonded to just two sides, it would get two hydrogen atoms. If a carbon is bonded only to one side, it would get three hydrogen atoms. I hope you understand this ranking already because carbon is going to show exactly four bonds, no less, no more. That's how it works. I hope I'm clear so far. If you have any questions, you can ask them now before I move on. All right, great. All right, 14.2, homologous series of organic compounds. Now, I've used the word before. You already know that when we talk about homologous series, we're actually talking about a specific family. Now, you already know the four properties that affect a homologous family or homologous series. You know they have a specific functional group. You know that they have a general formula. You know that they have almost the same chemical properties, and you know they have a trending set of physical properties changing throughout the series in a proper trend. So you already are familiar to those four properties from the IGCSE. So moving on, if I talk about the word functional group that we're going to use a lot in these, then any particular atom or grouping of atoms or even type of bond, which the books usually don't write anymore, but it's still considered as a functional group. When I talk about particular atoms, let me tell you the functional groups that you're already familiar with are F or Cl or Br or I. If I combine them all into one category of X, you know, X represents all the halogens. Now, if I attach only one of them to a group, or an organic compound, let's say we have propene, CH3, propane, CH3, CH2, CH3. If I just take one hydrogen atom out and instead I connect a chlorine atom with it, with just this one atom, now this becomes not an alkane, but a halogenated alkane. And as soon as it turns into a halogenated alkane, the entire set of properties change. The reactivity of the compound also changes. So the physical set of properties, the chemical set of properties is going to change. I hope you do understand that as soon as we introduce in a halogen, which is actually a proper functional group, it turns into a halogenated alkane, and halogenated alkanes are actually very good solvents. They might be used as anesthetics, right? And they can also be important in terms of different other usages. such as dry cleaning agents. So the set of uses, the reactivity, the chemical reactions themselves, their different kinds, I mean, all the physical properties, all of them change with just replacing one atom in the series. That atom can be considered as a functional group because that represents an actual class of compounds or a homologous series. It can be a grouping of atoms. If I do the same with propane, and this time instead of replacing it with just one atom of halogen, I replace it with an entire group of atoms like OH. Now you do understand OH immediately converts it into a category we call alcohols. Now, alcohols have their own usages. Yeah, they can be solvents, they can be used for alcoholic purposes, they have their own set of reactions, own set of physical and chemical properties. So I hope you do understand that a single atom or a group of atoms can be known for a functional group for a reason. But I'm going to also add type of bond to this list because if I don't just talk about other compounds, if I simply talk about the difference of alkanes, hydrocarbons I'm going to talk about. So alkenes and then with alkynes, I hope you do understand that we are not introducing a third atom in there. And the sole difference between these three functional groups is that all carbon atoms are singly bonded. There should be at least one double bond for alkenes, and there should be at least one triple bond for alkynes. That's how it goes. All right. So type of bond may also divide the category of compounds into different homologous series. So that's how we define functional group. So for a specific type of bond, for a specific group of atoms, for a particular atom, it can act as a functional group and it can actually define the type of series it is or may impart specific set of physical and chemical properties to it. All right. They have given examples of double bond or the formula, the carboxylic group already, which you're familiar. So the general formula of some homologous series, something we're going to discuss. This is going to be an entire set for AS and A2. So if you remember them, that's good. But remember, we're not going to use all of them right here and here. So moving on, you are going to see a big table. Where is the table, by the way? I thought there is a table right next to it. Oh, yeah, the table is a little bit farther. So I'm going to take you to the table first. Okay, so you're already familiar with alkanes. Let's talk about alkenes. So alkenes, at least a double bond, CnH2n, ethene, CH2 double bond CH2. So it represents general formula in the second column, an example in the third column, and structural formula of the same example from the third column. Halogenalkanes or halogenated alkanes or alkyl halides. All these names are for the same series, so do not get confused if a different set of naming is used or if a different general name is used. So X is really F, Cl, Bri, all of them. It gives you the idea CnH2n plus 1X, chloromethane, how the naming goes, of course. We are going to discuss that since I skipped the naming part, so I am going to discuss it later. Now, CH3Cl, alcohols, ROH, the same pattern, but instead of X, we have OH over here. Methanol, I'm going to discuss the naming for this one, CH3OH. Now, these were all that you were already familiar with. Let's talk about something that you're not familiar with, aldehydes and ketones. Now you're going to notice something that aldehydes and ketones might work in the same way. This is carbon doubly bonded oxygen in the center. And if both sides are R or alkyl groups, R means alkyl group. So if both sides are alkyl group, it's a ketone. If one side is an alkyl group and the other side is just hydrogen atom, it's aldehyde. Aldehydes are represented by this functional group. This entire is considered as a functional group. And ketones are represented by this functional group, so this just central part is considered as a functional group. Aldehydes have the suffix Al, and ketones have the suffix ONE. Now notice both sides of ketone work in the same way. They may not exactly be the same number of carbon atoms, but both the sides are CnH2n plus 1 or CmH2n H2n plus 1. That's how it goes. Okay. So apart from esters, ketone is going to be the second homologous series or type of a homologous series in which really the functional group stands in the exact center that you have already done with esters. Remember, there it was COO, the ester group in the center, and then there was a carbon chain over here, and then there was a carbon chain over here. That's how esters were supposed to be. Now this time it's just CO, and then there is a carbon chain on the right and on the left side of the whole structure. Those carbon chains can be the same, those can be different. So yeah, it works like that. Okay. So moving on, carboxylic acid, COOH, you're already familiar with this one. Now this might get a little tricky. They might take it as COOH separately, like this. Okay. And for, let me come to this one. Got to mention this. Okay. This can also be written, though this is the right way, but sometimes you would notice the NH2N plus 2O. This H is sometimes added to this one, makes it a whole formula of alkane, and then there's just the oxygen atom. But this is a better way to write it. This specifies the functional group OH as a part of the homologous series. But even if it is written like this in exams, which you are going to face a lot in paper one, don't get confused by it. Okay. So you might see the same thing over here. They might turn this into a different approach. So yeah, that is possible. Okay. Moving on, esters, CnH2n plus 1, CmH2n plus 1, COO in the center. Now, this might be shortened down as CO2H, or this might be shortened down as CO2 in the center, and then CmH2m plus 1 and CnH2n plus 1. So it might be shortened down to the COO, CO2 instead of COO. Don't get confused by it, it's the same thing. Amines, RNH2. Take one hydrogen out of ammonia, it turns into an amine. The amine can be connected to any functional, any organic compound because of the functional group of amine. Amines can be of different types. We're really going to discuss that at the mines chapter. Most of the mines portion is a part of A2, but some of the discussion also comes as a part of AS. We'll discuss that later. Now, this is a different kind of naming. You'll notice that we have named the R part first, and we simply write the word amine after. So methylamine, propylamine, ethylamine, that's how the name works. Okay. Nitriles, C triple bond N, and there is an R group before. So it is going to work in the same way. But this time, since just like carboxylic acids, carbon is also a part of the functional group. So that carbon has to be counted. Okay. So in this case, both the carbons will be counted and it would be ethane nitrile. Remember, it's not methyl nitrile, it's ethane nitrile. That's how this works. This naming can be a little bit confusing, but make sure you don't make the mistake. I'll discuss it in naming again so that you don't have a problem. Now, coming back to naming, okay. We had stem names, we had prefixes, and we had suffixes. Back in IGCSE, we're going to use the same. And now the prefixes really stick to from meth to hex, from 1 to 6 back in IGCSE. But I have explained this to my students all the way to dec or carbon 10, uh, even in IGCSE. So we're going to use that here in AS as well. So I hope you are clear with the prefixes already. As far as suffixes are concerned, you are familiar with most of the suffixes from IGCSE, at least alkanes for ane, alkenes for ene, alkynes for yne, or OL for alcohols, or OIC acid for carboxylic acids, or OH for esters. So you already probably be familiar with that. Well, what is going to be different at this stage is that we can have multiple branches in one compound in one chain. So how to convert that a structure into a name back to a structure is an important point. So let's talk about converting a structure into a name. And I am going to open whiteboard for that purpose. Let's go for a little bit of practice. I want to make sure that everyone is on the same page in this class. Okay. So to start with the simpler ones, the ones back in IGCSE usually had just one branch, and that's easy. You can always work that out. Apart from a couple of tricks, the ones that with single branches are always the easier ones to solve. So how about ladies first? What is the name of this compound? Ali, you can start working on the name of the compound and by yourselves,
Yeah.
and as soon as she's done with it, you're also supposed to answer after. And it's okay if you don't understand it or if you don't know how to name it. That's fine. You can say that completely all right if you have forgotten it. Not everyone is a fond of chemistry enough to remember everything back from IGCSE. It's completely okay. It's pretty normal if you don't remember it. Let me tell you. And that's not a joke. That is something that I keep saying in my classes that if you're a normal person, you'll tend to hate chemistry or dislike for few of its things, or you would simply don't understand or remember them after a while you've gotten rid of them or skip them for some time. So that's pretty normal. And only in the case if you're a normal person like me, you'd love chemistry and you remember the rules. So Laiba's back. Okay, so since I was asking the ladies, so that also includes you, Laiba. What is the name of this compound? I've asked already, Iman already, and the girls are going to tell me the name first. After that, I'm going to move towards them. Who's probably ready to tell the name, by the way? Seems so. Okay, it's up to you, girls. आवाज बहुत कम आ रही है. I was able to hear 2-methyl, but nothing after that.
2-methyl propane.
Perfect. 2-methyl propane. So how do you come up with a name?
2 per methyl group लगा हुआ है and then the straight chain is propane.
Perfect. Okay, so that is a very good way of doing it. You always mark the straight chain out. आप लोगों की different straight chains हो सकती हैं. Since there are 3 different chains possible, I'm just going for the obvious one. You can start numbering from the either side. That's worked well. ठीक है. तो हमारे पास ये 2 3 numbering हो गई. This is really the branch. So 2 is the number at which the branch is located, right? Meth means one carbon atom. All means that represents branch or alkyl group. Okay? Prop means three carbon atoms, and ane means they are singly bonded. So every part of the name has a purpose. I always keep saying the same thing. By breaking the name down into different parts, when you are so going for the opposite, trying to draw a structure from the name, it would be easier for you to work it out. Remember, you start writing the name from the left all the way to the right, but when you're going to break down a name into a structure, and when you're going for the opposite, really, it's always better to start from the right hand side first. I mean, you go for the skeleton first and then you go for the other parts. For example, work out propane first, then the methyl part, then two and the methyl part onwards. All right. Propane means three carbon atoms. So draw a skeleton for three carbon atoms. In means singly bonded. I've already done that. Then there is two methyl. So that's one, that's two, that's three. So meth, one carbon atom. I'll means alkyl group. So singly bonded. So that gives us the whole idea of the skeleton. Now you can go ahead and you can simply put up the hydrogen atoms, and this name is converted back into structure. That's how it goes. Okay. Now, I am going to go with a really neat trick. Okay, so back to the structure. This time, not the ladies first. This time, Ali, it's your turn. Okay, I've played a neat trick, and that trick is to just to deceive you with the naming part. The rest is fine. It's really the all the rules are same. It's just the trick that is might make the whole naming part difficult for you. Girls, you can keep working on by yourselves, and as soon as Lily comes up with a name, you need to confirm whether he's right or wrong. Okay, so I have three messages. No, Laiba, that's not correct. Need to work this one out. You actually fell for the trick. That's not the right name. GLE. Are you still looking at it?
Yeah, but I'm not getting anywhere.
Any ideas?
No.
Okay. So most of the time, what students fall for, which Laiba also did, is that they go for the obvious straight chain. But let me tell you, if you go for this obvious straight chain, then you have one, two, three, four, five carbon atoms, which is not right. Let me clarify. How is that not right? Because if you are going to work the chain a little bit differently, maybe like this, then you're going to notice you're not going to end up with five carbon atoms, you're going to end up with six carbon atoms instead. You might have worked it out a little bit differently. You might have worked it out like this. Let me tell you, both ways, either the red or the black is really fine. And both ways, you're going to end up
Yeah.
with six carbon atoms. Now, really, to start numbering for which side, and let me tell you, for both the red and for the black, you can't start from the downward side, because if you do, this is going to be one, this is going to be two, this is going to be three, this is going to be four, to which the branch is connected. For black, this is the branch. For red, this is the branch. And really, the number is same for both the black and red. So this kind of numbering is really incorrect. You can't go with this numbering. What I'm going to do is that I'm going to number it a little bit differently. Let's use this color, one, two, three, and this one's four, this one's five, and this one's six. That's actually the correct set of numbering. So it's going to be three, and then it's going to be ethyl, since these are two carbon atoms, one, two, so ethyl, and then hexane. It's not a propane, it's a hexane. Let me clarify the number to which the carbon atom, the branch is connected. Eth means two carbon atom, ethyl means singly bonded, and also that it's a branch. Ethyl actually represents both. Hex means six carbon atoms, and ane means singly bonded. Also, ane means that it is the part of parent chain, because I'll comes first, represents the branch, in comes after, represents the parent chain. All right, that's how it works. So the most obvious thing that sometimes we fall for is that we tend to locate the straight longest chain properly, improperly. Okay, get the point?
Yes.
So always go for the straight longest chain, but the carbon atoms should be directly connected, and you can't repeat a carbon atom in your numbering. The chains can't be taken as you go this way and then right, moving on from there you go this way and cover this one up as well. You can't do that. You can't include carbon atoms twice, right? So whatever is left out tends to be the branch, like this one was in our case. The good part about this kind of numbering is that you can start from the or numbering or locating the straight chain, is that different students may come up with different parent chains and different branches, but name is every time going to be the same. So if one student comes up with the black one I mentioned, and one student come up with the red one I mentioned, both will end up with the same name, 3-ethyl hexane. You can try it for yourself. You'll see that you end up in the same name, and that's what is the best part about nomenclature. Okay. Since it's about time, so I am right now not explaining the nomenclature of having multiple branches. Maybe multiple branches have a few cases, branches on different carbon atoms, branches on the same carbon atom. So we're going to do that, but this is what we're going to start with in the next setting. Any questions so far?